Studies Section 3, Multivariate Differential Calculus. Introduction. Earlier discussion at the lower class on differential calculus was based on single variable. In comparative static analysis, however, it is usual to come across a situation in which we have several variables and parameters so that the equilibrium value of each endogenous variable may be a function of more than one variable or parameter. To this end, we need to learn how to find the derivative of functions having more than one variable. This chapter deals with comparative static models with more than one variable. Objectives. At the end of this study section, you should be able to 1. Find the rate of change of any parameter in a multivariate model. 2. Differentiate between constrained and unconstrained optimization. 3. Identify and operationalize a set of rules that can be used to solve unconstrained and constrained optimization problems in a multivariate model. And 4. Analyze comparative static of any economic models. Pretext. 1. Given y equal to f bracket open, a, comma, b, bracket closed, is equal to bracket opened, a plus 2, bracket closed, bracket opened, 3a plus 7b, bracket closed. Find the partial derivatives of the function. 2. Given the demand and supply equations, QD is equal to A minus B P. QS is equal to minus C minus D P. Find the equilibrium prices and quantities. Find the rate of change. In price with respect to parameters A, B, C, and D, interpret your results. Content. Partial derivative. Consider the function y is equal to f into bracket z1, z2, z3 to zn, equation 3.1, where zi, brackets open, I is equal to 1, 2, 3, n, bracket closed, are all exogenous variables such that each can vary by itself without affecting others. If Z1 undergoes a change, delta Z1, say, while others remain fixed, there will be a corresponding change in Y, namely delta Y. Thus, the process of examining a change in Y with respect to a change in Z1, holding other variables constant, is called partial differentiation. In particular, partial differentiation differs from other differentiations because we must hold n-1 exogenous variable constant while allowing one variable to vary. To differentiate partial derivative sign from other signs, it is conventional to use curved D. That is the illustration 1. Consider the function y equal to f into bracket z1, z2 is equal to 3z1 squared, z2 cubed. Let us assume we want to consider a change in y as a result of a change in z1. We will treat z2 constant by mentally bracketing it with the coefficient. Y is equal to 3z1 squared, z2 cubed. Curved dy over curved the z1 is equal to y1 is equal to bracket open 3z2 cubed bracket closed d over the z1 bracket open z1 squared bracket closed is equal to 3z2 cubed times 2 is equal to 6z2 cubed. To examine the change in y with respect to change in z2, we treat z1 as a constant and follow the procedure above. Partial the y partial the z2 is equal to y2 is equal to bracket open 3z1 squared bracket closed d over the z2 bracket open z2 cube bracket closed is equal to bracket open 3z1 squared bracket closed dot 3z2 squared is equal to 9z1 squared z2 squared. Illustration 2. Find the partial derivative of the following function: y equal to f into bracket x, comma z bracket closed is equal to 5x cubed minus 3x squared z squared plus 7z raised to power 5. Partial the y over partial this x is equal to d dx into bracket 5x cubed minus 3z squared d dx s squared plus d dx 7z raised to power 5 is equal to 15x squared minus bracket opened 3z squared bracket closed dot 2x plus 0 y0 partial the y partial this x is equal to 15x squared minus 6z squared x partial the y dz is equal to d dz into bracket 5x raised to power 5 bracket closed minus bracket open 3x squared bracket closed partial d dz bracket open z squared bracket closed plus d dz bracket opened 7z raised to power 5 bracket closed is equal to 0 minus bracket opened 3x squared bracket closed dot 2z plus 35z raised to power 4. Partial the y dz is equal to minus 6x squared z plus 35z raised to power 4. Rules for partial differentiation. 1. Product rule. Given y equal to f into bracket x1 comma x2 bracket closed dot g into bracket x1 comma x2 bracket closed partial the y the x1 is equal to f into bracket x1 comma x2 bracket closed partial the g the x1 plus g into bracket x1 comma x2 bracket closed partial the f over the x1 equation 3.2 partial the y the x2 is equal to f into bracket s1 comma s2 bracket closed dot partial the g the s2 plus g into bracket s1 comma s2 bracket closed partial the f the s2 equation 3.3. Example: given y equal to bracket open 3x1 plus 5 bracket closed bracket open 2x1 plus 6x2 bracket closed. In this case, f into bracket x1 x2 is equal to 3x1 plus 5 into brackets, while g into bracket x1 x2 is equal to 2x1 plus 6x2 in brackets. Invoking product rule, partial the g the x1 is equal to 2, partial the f the x1 is equal to 3, partial the g the x2 is equal to 6, partial the f the x2 is equal to 0. Hence, by equations 3.2 and 3.3, partial the y the x1 is equal to bracket open 3x1 plus 5 bracket closed dot bracket 6 plus 2x1 plus 6x2 in bracket into bracket 3 is equal to 6x1 plus 10 plus 6x1 plus 18x2. Partial the y the x1 is equal to 12x1 plus 18x2 plus 10. Partial the y the s2 is equal to bracket open 3x1 plus 5 bracket closed into bracket 6 plus 2x1 plus 6x2 into bracket then bracket 0 is equal to 18x1 plus 30 plus 0 is equal to 18x1 plus 30. 2. Quotient rule. Y is equal to f into bracket s1 s2 over g s1 s2. G into bracket s1 s2 is not equal to 0. Partial the y the s1 is equal to g into bracket x1 s2 bracket closed partial the f the x1 minus parenthesis open f into bracket s1 s2 bracket closed partial the g partial the s1 parenthesis closed over parenthesis open g bracket open x1 x2 bracket closed parenthesis closed squared equation 3.4. Partial the y over partial the x2 is equal to g into bracket s1 s2 dot partial the f over the s2 minus parenthesis open f into bracket s1 s2 bracket closed partial the g partial the s2 parenthesis closed over parenthesis open g bracket open x1 x2 bracket closed parenthesis closed squared equation 3.5. Example, let y equal to 6x1 plus 7x2 in bracket over 5x1 plus 3x2 in brackets. Find the partial derivatives of the function. From the problem, we know that f of s1 s2 in bracket is equal to 6x1 plus 7x2 in bracket. G in bracket x1 x2 is equal to 5x1 plus 3x2 in brackets. Thus invoking quotient rule given by equations 3.4 and 3.5. Partial df over partial ds1 is equal to 6. Partial df over partial ds2 is equal to 7. Partial dg over partial ds1 is equal to 5. Partial dg over partial ds2 is equal to 3. Hence, partial dy over partial ds1 is equal to 5x1 plus 3x2 brackets dot 6 minus parenthesis opened bracket open 6x1 plus 7x2 bracket closed dot 5 parenthesis closed over 5x1 plus 3x2 in bracket squared is equal to 30x1 plus 18x2 minus 30x1 minus 35x2 over 5x1 plus 3x2 in bracket squared is equal to 18x2 minus 35x2 over 5x1 plus 3x2 in bracket squared. Partial dy over partial dx1 is equal to minus 17x2 over 5x1 plus 3x2 to bracket squared. Partial dy over partial ds2 is equal to 5x1 plus 3x2 in bracket dot 7 minus parenthesis open, bracket opened, 6x1 plus 7x2, bracket closed, dot 3, parenthesis closed, over 5x1 plus 3x2 in bracket squared is equal to 35x1 plus 21x2 minus 18x1 minus 21x2 over 5x1 plus 3x2 in bracket squared is equal to 35x1 minus 18x1 over 5x1 plus 3x2 into bracket squared. Partial dy over partial dx2 is equal to 17x1 over 5x1 plus 3x2 into bracket squared. 3. Generalized function. Rule. Given y parenthesis open f into bracket s1 s2 bracket closed parenthesis closed raised to power n. Partial dy over partial the s1 is equal to n parenthesis open f into bracket s1 s2 bracket closed parenthesis closed raised to power n minus 1 partial df over partial ds1 equation 3.6. Partial dy over partial ds2 is equal to n parenthesis open f into bracket s1 x2 bracket closed parenthesis closed raised to power n minus 1 partial df over partial ds2 equation 3.7. Example: find the partial derivatives of the function y equal to x1 cubed plus 7x2 raised to power 4 brackets raised to power 5. In the above example, partial df over partial dx1 is equal to 3x1 squared. Partial df over partial ds2 is equal to 28x2 cubed. Partial dy over partial ds1 is equal to 5 parenthesis open bracket open x1 cubed plus 7x2 raised to power 4 bracket closed raised to power 5 minus 1 parenthesis closed into bracket 3x1 squared bracket closed. Partial dy over partial ds1 is equal to 15 into bracket 3x1 squared bracket closed into bracket x1 cubed plus 7x2 raised to power 4 bracket closed raised to power 4. Partial dy over partial ds2 is equal to 5 parenthesis open bracket open x1 cubed plus 7x2 raised to power 4 bracket closed raised to power 5 minus 1 parenthesis closed bracket open 28x2 raised to power 3 bracket closed. Partial dy over partial ds1 is equal to 140x2 cubed into bracket 28x2 raised to power 3 bracket closed. Partial dy over partial ds1 is equal to 140x2 cubed into bracket x1 cubed plus 7x2 raised to power 4 bracket closed raised to power 4. Application to economics. 1. Consider a simple one commodity market model, in which case the demand and supply equations are given as follows. QD is equal to A minus BP. QS is equal to minus C plus DP. The equilibrium solutions are P asterisk is equal to A plus C over B plus D. Q asterisk is equal to AD minus BC over B plus D. Now let us consider how a change in each of the parameters will affect the equilibrium price. To do this, we will partially differentiate P asterisk with respect to each parameter. Note that we have 4 parameters that determine the equilibrium price. Therefore, we shall establish 4 partial derivatives. Which rule are we going to invoke? Quotient rule, of course. Hence, we let f into bracket s1 s2 is equal to a plus c, while g into bracket s1 s2 is equal to b plus d. By equation 3.4 and 3.5, partial the p hysteresis over partial the a is equal to bracket open b plus d bracket closed dot 1 minus parenthesis open bracket open a plus c bracket closed dot 0 parenthesis closed over b plus d in bracket squared is equal to b plus d over b plus d in bracket squared. Partial the p hysteresis over partial the a is equal to 1 over b plus d greater than 0. Partial the p hysteresis over partial the b is equal to bracket b plus d bracket 0 minus parenthesis open bracket open a plus c bracket closed 1 parenthesis closed over b plus d in bracket squared. Partial the p hysteresis over the b hysteresis is equal to minus a plus c over b plus d in bracket squared less than 0. Partial the p hysteresis over partial the c is equal to bracket open b plus d bracket closed 1 minus parenthesis open bracket open a plus c bracket closed 0 parenthesis closed over b plus d in bracket squared is equal to 1 over b plus d greater than 0. Partial the p hysteresis over partial the d is equal to minus a plus c over bracket open b plus d bracket closed squared less than 0. Hence, partial the p hysteresis over partial the a is equal to partial the p hysteresis over partial the c is equal to 1 over b plus d greater than 0. Partial the p hysteresis over partial the b is equal to partial the p hysteresis over partial the d is equal to minus into bracket a plus c over b plus d into bracket squared less than 0. That is, an increase in A, the intercept of demand, on an increase in C, the intercept of supply, will, holding other things constant, increase equilibrium price. Conversely, an increase in B, the slope of demand, or an increase in D, the slope of supply, will, holding other things constant, reduce equilibrium price. Since A and B appear in the demand equation, it means that changes in either of the two will affect the demand curve only. How will the effect take place? We know that A is autonomous while B is induced. Therefore, a change in equilibrium price with respect to a change in A will shift the demand curve parallel to itself, while a change in equilibrium price caused by a change in B will pivot the demand curve inward or outward depending on whether such change is an increase or a decrease in B. We also know that C and D are parameters appearing in the supply equation. Hence, a change in equilibrium price caused by changes in any of the two will affect the supply curve only. Since C is an exogenous parameter, a change in equilibrium price with respect to C will shift the supply curve parallel to itself, while a change in equilibrium price as a result of changes in D will pivot supply curve inwards or outwards depending on whether such a change is an increase or decrease in D. 2. A certain consumer consumes 2 goods, rice and beans. The utility derived from the 2 goods are given as follows. U is equal to bracket open 3b squared plus br plus 2r cubed bracket closed raised to power 4, equation 3.8. Assuming that B is equal to 3 and R is equal to 2, determine the marginal utilities of beans and rice consumed by the consumer. The rule to apply for finding the marginal utilities of the consumer is Rule 3, the generalized function rule, using equations 3.6 and 3.7. Partial du over partial db is equal to 4 bracket open 3b squared plus br plus 2r cubed bracket closed raised to power 3 bracket open 6b plus r bracket closed. Partial du partial db is equal to bracket open 24b plus 4r bracket closed bracket opened 3b squared plus br plus 2r cubed bracket closed raised to power 3. Partial du partial dr is equal to 4 bracket open 3b squared plus br plus 2r cubed bracket closed raised to power 3 bracket open r plus 6r squared bracket closed. Partial du partial dr is equal to bracket open 4r plus 24r squared bracket closed bracket opened 3b squared plus br plus 2r cubed bracket closed raised to power 3 with b is equal to 3 and r is equal to 2. Partial du partial db is equal to parenthesis open 24 bracket open 3 bracket closed plus 4 bracket open 2 bracket closed parenthesis closed parenthesis open 3 bracket open 3 bracket closed squared plus bracket open 3 bracket closed bracket open 2 bracket closed plus 2 bracket open 2 bracket closed raised to power 3 parenthesis closed raised to power 3 is equal to parenthesis open 72 plus 8 parenthesis closed parenthesis open 27 plus 6 plus 16 parenthesis closed raised to power 3 is equal to bracket open 80 bracket closed bracket open 49 bracket closed raised to power 3 is equal to 80 in bracket times 117649 in bracket. Partial du partial db is equal to 9,411,920 utils. Partial du partial dr is equal to parenthesis open 4 into bracket 2 plus 24 into bracket 2 squared parenthesis closed parenthesis open 3 into bracket 3 squared plus 3 in bracket 2 in bracket plus 2 into bracket 2 raised to power 3 parenthesis closed raised to power 3 is equal to bracket open 8 plus 96 bracket closed bracket open 27 plus 6 plus 4 bracket closed raised to power 3 is equal to 104 in bracket 37 in bracket raised to power 3 is equal to 104 in bracket 50653 in bracket. Partial du partial dr is equal to 5,267,912 utils. 3. Let the production function of a particular firm exhibit Cobb-Douglas production function of the form Q is equal to AK raised to power alpha L raised to power beta. Alpha plus beta is not equal to 1. Find the marginal product of labor and capital. The appropriate rule for solving this problem is the product rule. So we use equations 3.2 and 3.3. MPK is equal to partial dq partial dk is equal to bracket open AL raised to power beta bracket closed d dk k raised to power alpha is equal to AL beta alpha k raised to power alpha minus 1 is equal to alpha A L raised to power beta k raised to power alpha minus beta is equal to alpha A L raised to power beta k raised to power alpha over k. MPK is equal to alpha q over k. MPL is equal to partial the q partial the L is equal to A k raised to power alpha in bracket d the L raised to power beta is equal to bracket open A k raised to power alpha bracket closed beta L raised to power beta minus 1 is equal to A k raised to power alpha beta L raised to power beta minus 1 is equal to beta A k L raised to power beta minus 1 is equal to beta A k raised to power alpha L raised to power beta over L. MPK is equal to beta q raised to power L. 4. Let the utility function of a consumer exhibit constant elasticity of substitution, CEF, utility function of the form U is equal to U parenthesis open alpha x1 raised to power minus beta plus bracket open 1 minus alpha bracket closed x2 raised to power minus beta parenthesis closed raised to power minus 1 over beta, equation 3.9, where x1 and x2 are commodity bundles consumed and alpha and beta are structural parameters. Find the marginal utility of goods x1 and x2 if alpha and beta are 0.4 and 0.6 respectively and x1 and x2 are 10 and 8 units respectively. This problem requires invoking rule 3. First, we apply equation 3.6 and 3.7. Partial the f partial the x1 is equal to minus alpha beta x1 raised to power minus into bracket beta plus 1. Partial the f partial the s2 is equal to minus beta into bracket 1 minus alpha bracket closed x2 raised to power minus into bracket beta plus 1 bracket closed. Partial u partial x1 is equal to minus 1 over beta parenthesis open alpha s1 raised to power minus beta plus bracket open 1 minus alpha bracket closed s2 raised to power minus beta parenthesis closed raised to power bracket open minus 1 over b bracket closed minus 1 into bracket alpha beta s1 raised to power minus beta minus 1 bracket closed is equal to minus 1 over parenthesis open alpha x1 raised to power minus beta plus bracket open 1 minus alpha bracket closed s2 raised to power minus beta parenthesis closed raised to power minus bracket open 1 plus beta bracket closed over beta into bracket minus alpha beta s1 raised to power minus bracket open beta plus 1 bracket closed and bracket closed. Partial u partial s1 is equal to alpha s1 raised to power minus b plus 1 parenthesis open alpha s1 raised to power minus beta plus bracket open 1 minus alpha bracket closed x2 raised to power minus beta parenthesis closed raised to power minus bracket open 1 plus beta bracket closed, over beta. Partial u partial s2 is equal to minus 1 over beta, parenthesis open, alpha s1 raised to power minus beta plus bracket open 1 minus alpha bracket closed s2 raised to power minus beta parenthesis closed raised to power minus 1 over beta into bracket minus 1 parenthesis open beta into bracket 1 minus alpha bracket closed x2 raised to power minus beta plus 1 in bracket parenthesis closed is equal to minus 1 over beta parenthesis open alpha s1 raised to power minus beta plus bracket open 1 minus alpha bracket closed s2 raised to power minus beta parenthesis closed raised to power minus into bracket 1 plus beta over beta parenthesis open beta into bracket 1 minus alpha s2 raised to power minus into bracket beta plus 1 parenthesis closed. Partial u partial s2 is equal to parenthesis open bracket opened 1 minus alpha bracket closed s2 raised to power minus into bracket beta plus 1 bracket closed parenthesis opened alpha s1 raised to power minus beta plus bracket opened 1 minus alpha bracket closed s2 raised to power minus beta parenthesis closed raised to power minus into bracket 1 plus beta over beta with alpha equal to 0.4, beta equal to 0.6 and s1 equal to 10 while s2 is equal to 8. Then marginal utility of goods s1 will be partial u partial s1 is equal to 0.4 into bracket 10 raised to power minus into bracket 0.6 plus 1 parenthesis open 0.4 into bracket 10 raised to power minus 0.6 plus bracket open 1 minus 0.4 bracket closed 10 raised to power minus 0.6 parenthesis closed raised to power minus into bracket 1 plus 0.6 over 0.6 is equal to 0.4 into bracket 10 raised to power minus 1.6 parenthesis open 0.4 into bracket 10 raised to power minus 0.6 plus 1 minus 0.4 into bracket 10 raised to power minus 0.6 parenthesis closed raised to power 1.6 over 0.6 while marginal utility of good s2 will be partial u partial s2 is equal to parenthesis open bracket open 1 minus 0.4 bracket closed bracket open 8 bracket closed raised to power minus 0.6 plus 1 in bracket parenthesis closed parenthesis opened 0.4 into bracket 10 raised to power minus 0.6 plus 1 minus 0.4 in bracket 10 raised to power minus 0.6 parenthesis closed raised to power minus 1 plus 0.6 in bracket divided by 0.6 is equal to 0.6 into bracket 8 raised to power minus 1.6 parenthesis opened 0.4 into bracket 10 raised to power minus 0.6 plus bracket 1 minus 0.4 10 raised to power minus 0.6 parenthesis closed raised to power minus 1.6 over 0.6. Total differentials. In our partial differentials, we look at how a change in one parameter affects the endogenous variable, holding other parameters constant. In this section, we relax the assumption of holding other parameters constant. That is, we ask how the endogenous variable changes will give an infinitesimal change in all the parameters. Consider a saving function that is expressed as follows. S is equal to S into bracket Y I, equation 3.10, where S is total national savings, Y equals aggregate income, and I is the real interest rate. How will S change given an infinitesimal change in income and interest rate? This is solved by applying the following formula. ds is equal to partial ds over partial dy into bracket dy plus partial ds over partial di into bracket di. Dx is equal to sy dy plus si di, equation 3.11. The expression ds being the sum of the approximate change from both income and interest rate is called total differential of the saving function. The process of finding it is called total differentiation. We see that the sum of partial differential is actually the total differential of a function. In a more general case, a function with independent variables can be exemplified by, say, a utility function as in u is equal to u into bracket s1, s2, s3 to sn, equation 3.12. The u is equal to partial du partial ds1 ds1 plus partial du partial ds2 ds2 plus partial du partial ds3 ds3 plus dot 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 plus partial du partial dsn dsn is equal to summation I equal to partial dui over partial dsi dsi. Rules of total differential. Rule 1, decay is equal to 0. Rule 2, dcu raised to power n is equal to cn u raised to power n minus 1 du. Rule 3, d into bracket u plus or minus v is equal to du plus or minus dv. Rule 4, d into bracket uv is equal to v du plus u dv. Rule 5, du over v is equal to v du minus u dv over v squared. Examples. 1. Find the differential dy of the function y equal to 5x1 squared plus 3s2. We invoke rule 3. Dy is equal to partial dy over s1 ds1 plus partial dy over the partial s2 ds2, 3.13. Dy is equal to 10s1 ds1 plus 3ds2. 2. Find the total differential of the function y equal to s1 plus s2 over 2s1 squared. We make use of rule 5. We know that partial dy over partial ds1 is equal to minus x1 plus 2x2 into bracket over 2x1 cube. Partial dy over partial ds2 is equal to 1 over 2x1 squared. Hence, the y is equal to minus x1 plus 2x2 in brackets dx1 over 2x1 cube plus 1 over 2x1 squared dx2. Total derivatives. In some cases, it is possible to discover that one of the independent variables is actually dependent on another independent variable in the model. For instance, it will be misleading to find the rate of change in consumption C with respect to tax while holding income Y constant because tax and income are in some sense related. A tool used to solve this problem is the use of total derivative. To make things easy, consider this function y equal to f of x w, x is equal to h into bracket w. We can combine the two functions together to get y equal to f of h into bracket w, comma, w, then bracket closed, indicating that the three variables are related to one another. W affects y through direct and indirect channels. The indirect channel is through function h and the direct channel is through function f. Thus, the y dw is equal to partial dy partial dx, the x the y plus partial the y partial the w, equation 3.14, is equal to f of x, the x w, plus f w, indirect, direct. Example, find the total derivative of the function y equal to f of x w in brackets is equal to 3x minus w squared. X is equal to g function of w is equal to 2w squared plus w plus 4. Partial dy partial dx is equal to 3. The x, the w, is equal to 4w plus 1. Partial dy partial dw is equal to minus 2w. Hence, the y, the w, is equal to 3 into bracket 4w plus 1 plus minus 2w is equal to 12w plus 3 minus 2w. The y, the w, is equal to 10w plus 3. Application to economics. Let the production function of a particular firm be expressed as follows. Q is equal to Q into bracket K L T. That is, level of output depends on capital K, labor L, and time T. But capital and labor can also depend on time as well. That is, they vary with time such that K is equal to K into bracket T, L is equal to L of T. The rate of change of output with respect to time can be expressed as follows. The Q, the T, is equal to partial the Q partial the K into bracket, the K, the T, plus partial the Q partial the L into bracket, the L, the T, plus partial the Q partial the T, equation 3.15. Example, let Q is equal to A into bracket T, KL is equal to 4KL. K is equal to 5 plus 0.2 T. L is equal to 3 plus 0.6 T. Find the rate of change of output with respect to time. First find partial the Q partial the K, partial the Q partial the L, the K the T, the L the T, and partial the Q partial the T. Partial the Q partial the K is equal to 4L. Partial the Q partial the L is equal to 4K. The K, the T is equal to 0.2. The L, the T is equal to 0.6. And partial the Q partial the T is equal to 0. Plug this in equation 3.15. The Q, the T is equal to 4L into bracket 0.2 plus 4K into bracket 0.6 plus 0. The Q, the T is equal to 0.8L plus 2.4K. If the values of K and L are given, we can easily solve for the rate of change. This is the end of study section 3. Thanks for listening.